Hello. Here we're going to dive in to the beautiful world of astrophotovoltaics, or essentially the energy we see in the middle of the void of space. The solar energy keeping our satellites and telescopes alive in that quiet, dark solitude there. So, if we look outside, surrounding Earth's atmosphere, we'll see nearly 10,000 satellites in what we call low Earth orbit orbiting around Earth, and additional telescopes and all sorts of other human uses for essentially our technology as a society that we've sent out to space. And these technologies and these locations of which the satellites operate have air masses or atmospheres less than a billionth that of the ground on Earth, which makes lots of challenges for using solar technology and really powering these systems. And we have some great technology out there. However, a lot of it is what's made of what we call silicon, which is a very standard semiconducting material. It's fairly heavy, it's fairly maximized, and it's prone to what you see on the bottom here, or proton radiation. Through the cosmic radiation in space, protons can leave high levels of damage on silicon cells. And recent developments have shown a new type of semiconducting material that's lighter and cheaper and actually has self-healing properties that resist some of this radiation. And that's what we call perovskites and develop in our lab. If we look at a comparison of perovskites and silicon-based solar cells, we can see that perovskites typically have comparable efficiencies, but they're more flexible, they're lighter, they're cheaper, they're better optimized. Unfortunately, the one issue we see in perovskites is their durability, or specifically their degradation over time. Essentially, these are materials that are made in a lab, and they're made artificially as a replacement to silicon. Now, I would encourage you to feel free to reference any of the attached materials, portfolio, anything else for more details on some of the background to this description. But in general, when we're looking at this project and this idea of space-based research, our lab has developed these perovskites to be in this very ideal spot where we need to solve this one issue, and that is the durability and the degradation. And in our lab, we make our own perovskite cells that are called tandem or two-layer cells. So obviously in space, you don't have the ozone layer, and you have higher percent of ultraviolet or kind of intense light hitting your solar panels on satellites and telescopes. And so what we make is a tandem or two-layer solar cell in which one layer, a narrow versus wide band gap, focuses more on the visible light and other focuses more on closer to the UV light spectrum to really optimize efficiency for space-based conditions. And we make it in our lab with what you can see in the top right is a perovskite material. So we use specifically cesium-based perovskite materials. Again, all of this referenced in the paper and some of the attached materials. And we also use what's called P3CT and P.PSS, which are some polymers on the bottom here for our different separation layers to really maximize the charges. So let's dive into what's going on here in the lab. There's a few different snapshots I can show here. First of all, we make our devices, our cells, whatever you want to call it, our miniature solar panels in our lab with chemical coating and metal deposition techniques based on the materials you just saw. And they're stored in the top left in vacuum sealed chambers. Right, with this perovskite degradation, we want to assure ourselves that the lab measurements are kept safe and they're kept very, very well measured and accurate. And so we want to make sure that there's no humidity or temperature change or things like that, just in their storage damaging them. And so the cells or the devices that we're using, particularly for this project though, go into a kind of different type of atmosphere because we're trying to simulate these space-based, really harsh conditions. And so a few of the things you'll see here kind of do that. So for example, on the bottom right, you'll see external quantum efficiency, which is one of the key solar efficiency measuring systems. And essentially, it's looking at the ratio of photons absorbed to the electricity we're actually getting, and the what we call electrodes. And so essentially, we're looking at that. We're looking at essentially that by layers. We're looking at on the left side, you can see JV, or a common efficiency measurement, where we compare the space-based spectra of light with the higher UV component to some others, the Earth-based. And then again on the top, you can see a lab where we do our thermal cycling, or rapid temperature fluctuations, to model what happens deep in the outer bounds of space. So if we look at what we have actually seen here, we found some really exciting things. So for our JV plots, and again, more details, feel free to read, we can see some general efficiency measurements here. And VOC is called open circuit voltage, and it's generally proportional to power conversion efficiency. Kind of shows the potential of the cells. And so some of the first batch that we've made here, and this is a very new, novel kind of idea to use perovskites in space because of their degradation factors. And with this JV in our preliminary findings, we saw certain discrepancies and damages. They didn't look perfect, but we saw very strong results as a whole. And we noticed some, minor issues in our batches when we did those rapid temperature fluctuations, that thermal cycling. But when it really gets the information interesting is when we looked at some of our updated batches. So we improved our devices, and we saw not only just internal improvement, but actually some very high VOC levels, both before and after thermal cycling when compared to our preliminary trials. When we dive into what's more interesting here, though, is the EQE. And this is super cool because it's one of the higher regarded types of efficiency measurements in photovoltaics, where we can actually separate those two different layers and measure them differently based on their light compositions. And this was key because this told us, our devices were doing pretty well, and we had measured them in this new system, but this told us what was the one issue, the one thing we needed to tweak. And that, as you can see, is the narrow bandgap layer. So essentially, when you're looking at EQE, JSC, or short circuit current, similar to open circuit voltage like we discussed, it's a big measure of efficiency internally. And so both cells had done pretty good in both layers. However, the narrow bandgap, we can see lower JSCs, and specifically our bold lines, or our post-thermal cycled, so the cells we did those temperature fluctuations on, showing that damage. And so we were able to actually improve those cells and to do some updated batch findings where we had both strong JSC values at some of the highest standards we've ever been able to see for space-based considerations. The holy grail, the final answer, is that thing I've been hinting at, or that thermal cycling temperature fluctuation. So one of the central points of this idea of harsh UV light, but specifically the temperature fluctuating rapidly, is measuring from around 0 to 60 degrees Celsius, and eventually we actually expanded that. When solar panels, tilt out of the sun, satellites can change, and you see super big changes in temperature very fast. And so these are about 20-minute cycles. This is weeks of data, right? 900 plus cycles. And we were expecting about 75% retention. We were able to retain over 80% for this amount of pretty intense cycles. And even more exciting, like I said, we updated the batches, we developed some better devices, and we were able to see over almost 85% efficiency. So again, better than the 75%, better than we've really ever been able to see, and almost at the standards of just ground-based perovskite. So looking at this super intense, we went actually from negative 20 to 80 degrees Celsius here, hundreds of cycles, super intense light and temperature change, and we were able to actually identify just immense amounts of success and retention that we hadn't yet seen before. And so what this really tells us, and there's a hint here for future, is not only that we can do well in our cells, and that some of this research, the space-based research, is kind of at the top of the field and ready to be published, but really it shows us that our cells could be kept up. So all of the cells in the solar panels you would see in space are this silicon material, radiation damaged, heavier, and with perovskites having enough retention of their efficiency, right, with minimized degradation like we've seen, we're actually shifting into a new realm where we might be able to commercialize these devices and really put these new and improved energy systems in space. And this chart here just shows even better optimism, where we can see batches as we've developed in our lab increasing just their general ground-based EQE efficiency levels on both layers. So as we keep up these cells with our thermal cycling and eventually go to that commercialization publication stage, we've seen really just some amazing improvements on our cells. So last thing is really just why. Why are we doing this? And I briefly mentioned at the beginning, essentially, we're making lighter, cooler cells. But the reality of it is you don't have a lot of options in space. You really only have solar technology on these really cool pieces of equipment that are isolated by themselves in this void of cold space conditions. And so when we develop these devices, we not only create better systems of this energy deployment, but we're able to expand humanity's reach across the solar system and the galaxy as a whole.